Hello everyone. In this lecture I'm going to continue on with concepts in renal physiology, and specifically I'm going to be talking about intrinsic mechanisms that control GFR, or glomerular filtration rate, which is a flow in mils per minute. Alright, but before I get to the intrinsic mechanisms that control GFR, let me just first review those 4 different processes of urine production. The first one is filtration, which I'll go into a little bit more detail in the next few slides. However, if you're still confused or a little fuzzy about reabsorption, secretion, and excretion, please refer back to the video on Intro to Renal Physiology. Alright, so let's take a look again at the anatomy of the glomerulus. This is the glomerular capillaries right here in the center, and they're surrounded by Bowman's space and Bowman's capsule here. So this is the single unit of filtration that we've already talked about. Blood actually enters into the glomerular capillaries by this afferent arterioles. And you can see there's a lot of smooth muscle that surrounds these arterioles. The blood enters into the glomerulus via these afferent arterioles. And then you can see here all of this red area are the glomerular capillaries. They are under very high pressure. We've already gone through this particular slide as well. You can actually see that the blood pressure, in the hydrostatic pressure in the glomerular capillaries, is very high at 60 millimeters of mercury. That's twice as high as a lot of the capillary beds in the vasculature, which usually only top out at about 33 millimeters of mercury. So this is really important. These glomerular capillaries, right here in red here, are under very high pressure. That always ensures that the blood is filtered out of the glomerular capillaries into Bowman's space. So usually the larger blood proteins like erythrocytes, red blood cells, and albumin stay inside the capillaries, but what's forced out is smaller molecules, electrolytes, and fluid. So the ultrafiltrate within Bowman's space is usually very plasma-like. Still under considerably high pressure, 16 millimeters of mercury, and that just ensures that the fluid keeps moving throughout the entire nephron. So going back to our figure, looking at the anatomy of the glomerulus, blood enters into the glomerular capillaries. It's actually forced out into Bowman's space. Now what you don't see here is the fluid actually enters into the proximal tubule. The loop of Henle is actually cut off. It actually extends all the way down into the intermedullary region. You're missing the thin descending limb and the thick ascending limb, and then it captures in this diagram the distal tubule. So the distal tubule is actually very closely associated with the glomerulus, and that's where we're going to start with the intrinsic mechanisms. You can actually see these specialized epithelial cells that line the distal tubule called the macula densa cells. And these cells are actually detecting the flow rate, the flow actually, through this tubule. And then it can send a signal to the afferent or efferent arterioles, right? The signals actually trigger vasoconstriction, these smooth muscle cells to contract, to increase the resistance to reduce flow into the glomerular capillaries. So there's a lot of signaling that goes on between the macula densa cells and these smooth muscle cells that surround the afferent arterioles. You'll also notice these pink mesangial cells. We'll talk about that as well. It's one of the 3 intrinsic mechanisms that I'll be talking about. And don't forget these podocytes here. Mesangial cells actually extend into the glomerulus. These are intraglomerular mesangial cells, and they're closely associated with the podocytes as well. So also, remember that if you constrict the afferent arterioles, it actually has dramatic effects on glomerular filtration rate. We've already gone through this slide as well. If you constrict afferent arterioles, it actually increases the resistance in that particular area, decreasing the hydrostatic pressure of the glomerular capillaries and effectively decreasing the flow, the glomerular filtration rate. If you dilate these afferent arterioles, the opposite occurs. You get an increase in the hydrostatic pressure in the glomerular capillaries and an increase in the flow, an increase in glomerular filtration rate. So just remember these plumbing issues, these concepts that we've learned in the previous section on Intro to Renal Physiology. So, the three intrinsic pathways that you need to know for this lecture are myogenic regulation, tubuloglomerular feedback, and mesangial control. These mesangial cells control glomerular filtration rate. We'll be talking about extrinsic endocrine hormones in the next lecture, which includes things like angiotensin, which is a powerful vasoconstrictor, or other molecules like prostaglandins that are vasodilators. All right, so let's start off first. Again, we're only going to go through these intrinsic pathways in this lecture: myogenic regulation, tubuloglomerular feedback, and mesangial control. The first one, myogenic regulation, is depicted in this left diagram, this flow diagram, and I'll blow this up so that you can actually see it a little bit better. Again, we're going to be concentrating on myogenic regulation first. All right, so let's go through this figure. This is a flow chart that is depicting, it's an example of myogenic regulation. Myo meaning it's referring to muscle, and it's referring to that smooth muscle that surrounds the afferent arteriole. Okay, so myogenic means it's referring to the muscle and the origin of the mechanism. So this is myogenic regulation. So in this case, if you have an increase in mean arterial pressure, a surge in high blood pressure, we're going to read down first. You're going to get an increase in the afferent arteriolar pressure, which is going to lead to an increase in glomerular capillary pressure and an increase in that net filtration pressure. Okay, so they depict it as glomerular filtration pressure, which is ultimately going to lead to an increase in glomerular filtration rate, which is flow. All right? Now, this regulation, this myogenic regulation, is an auto-regulation mechanism to try to keep GFR, the glomerular filtration rate, constant in the face of varying mean arterial pressure. Okay, so it's trying to keep the glomerular filtration rate within homeostatic ranges, within constant. Okay, so the mechanism is this. If you do get an increase in mean arterial pressure, a surge in that high blood pressure, it's going to cause, again, an increase in afferent arteriolar pressure, and it's going to stretch those smooth muscle cells that surround the afferent arterioles. Okay? With that stretch is going to actually activate some of those mechanoreceptors in the smooth muscle cells, and it's going to cause a compensatory constriction of the smooth muscle that surrounds the afferent arterioles. So you're going to get an increase in constriction of these afferent arterioles, an increase in the resistance at that site, which is going to lead to a decrease in glomerular capillary pressure, a decrease in the net filtration pressure, and ultimately a decrease in glomerular filtration rate. So again, this is a compensatory mechanism to try to keep GFR constant in the face of changing or varying arteriolar pressure, mean arterial pressure. Okay, trying to keep that GFR constant. All right, so now let's move on to tubuloglomerular feedback. This is the flow chart on the right-hand side of this particular figure. And let's review the anatomy of the glomerulus and the distal tubule one more time. All right, so let's review the anatomy here before we go on and talk about tubuloglomerular feedback. What's important with this slide is to understand the macula densa cells. You can actually see that within the distal tubules, right? These macula densa cells are specialized epithelial cells that detect the flow through the distal tubule. So if the flow is too slow or too fast, what's going to happen is the macula densa cells are going to send a signal to the smooth muscle cells that surround the afferent arterioles, and it's going to cause them to constrict. Again, you can imagine if the flow is too great, it's too fast through that area, sending a signal to those smooth muscle cells, causing them to constrict, is going to slow glomerular filtration rate and keep the flow through the distal tubule constant. However, it also works the opposite. If the flow through the distal tubule is way too slow, there is the same effect occurs, right? The smooth muscle cells that surround the afferent arterioles also constrict. And the logic behind that, when you're trying to learn this, is if you have such low blood pressure and the flow is so slow through the distal tubule, you don't want to lose any more fluid to your environment. So you constrict those afferent arterioles, decreasing glomerular filtration rate so that you're not filtering hardly anything at all, so you're not losing any fluids to your environment, excreting it. So again, those macula densa cells, they will cause constriction of the smooth muscle cells that surround the afferent arterioles if the flow through the distal tubule is too slow or too great. All right, so now let's take a look at this flow chart. Again, this is an example of tubuloglomerular feedback. In this case, the individual has a surge of high blood pressure, or at the top here, increase in mean arterial pressure. What that leads to is an increase in afferent arteriolar pressure, an increase in hydrostatic pressure of the glomerular capillaries, and then obviously an increase in net filtration pressure at the bottom here, glomerular filtration pressure, which ultimately leads to an increase in glomerular filtration rate or flow. All right, in this case, what's going to happen is these macula densa cells are going to detect that increase in flow, sending a signal to the smooth muscle cells that surround the afferent arterioles, causing constriction of the afferent arteriole, which leads to an increase in resistance of those vessels, which then in turn decreases glomerular capillary pressure and ultimately decreases glomerular filtration rate. All right, so the final intrinsic pathway that I want to go through is called mesangial control. You can actually see in this slide where the mesangial cells are. They're actually right here. These are the extraglomerular mesangial cells. They're responsible for reproportioning some of the blood volume in the glomerular capillaries through the actions of these mesangial loops. They also change capillary surface area, and the intraglomerular mesangial cells are very closely associated with the podocytes, and when they contract, they actually can decrease the filtration slits and have effects on glomerular filtration rate. So, the glomerular mesangial cells control blood pressure and glomerular filtration rate within the glomerulus. It has been shown that glomerular mesangial cells modulate the ultrafiltration of glomerular filtration rate, partly by changing the capillary surface area and partly by reproportioning blood volume in glomerular capillaries through the actions of mesangial loops. Also, as I talked about in the previous slide, mesangial cells can be closely associated with the podocytes to change filtration slits and also affect glomerular filtration rate. So, we've learned about the three intrinsic pathways: myogenic regulation, tubuloglomerular feedback, and mesangial control. Again, these are all autoregulation mechanisms that try to keep glomerular filtration rate constant. So again, why are these intrinsic pathways important? The answer is to keep glomerular filtration rate constant in the face of varying arteriolar pressure. So let me just show you the next slide to really bring this all home. And one more question, basic